Yeah, so good afternoon, everyone. I think the people are still connecting, but I will be first, thank you, all of you, for having registered to our webinar today on photocatalytic synthesis for a carbon neutral production of fuels and chemicals. Well, actually, we had a registration from people all around the world, so I will say good morning, good afternoon, and good evening, just in case. This webinar has been organized by the project SunCoChem, which is coordinated by EURECAT and that is receiving fundings from the European Union's Horizon 2020 Research and Innovation Program. And a special thanks to Marina Presas, our communication leader, who has been working very hard for this. Now I will give you a brief overview of the agenda now. So my name is Maria Navarro and I'm a SunCoChem project coordinator. I will be moderating the webinar today together with Ricard García Valls, who will give a brief speech about the topic of photocatalysis synthesis to put us in context. And then later on, Francesca Toma from the Lawrence Berkeley National Laboratory will give a presentation on the mechanism of photoelectrochemical transformations in functional architectures for artificial photosynthesis. We will then open a window of 10 minutes for questions and answers. Remember to use the tool of questions, not the chat, although we will be trying to see everything that you are commenting, but please use the tool of questions of this platform, go to webinar, and then we will be reading the questions in order of appearance. Then the next step will be the presentation of the 3 projects that were funded under the same topic of Horizon 2020, the NMVP 25-2019 called Photocatalysis Synthesis. Miriam Díaz de los Bernardos will do the presentation of SunCoChem. It will be about the concept underpinning the project, and a special mention to Simelis Hernandez, who is the SunCoChem technical coordinator. She's associate professor in the Politécnico de Torino, and she's also with us today. Next, Pau Farras will present the Flow Photochem. It's a project he's coordinating, and he will also explain us the novel concepts that they are embracing in this project. Last but not least, we will have Gabriel Senti presenting the project Decade. Yes, on the basis of what is this project about. And then we will open a window of 20 minutes for you to ask questions or start debating or discuss wherever it pops up to your mind with the speakers. In this occasion, for this second session of questions, please remember to type as well the name of the presenter, either Miriam or Pau or Gabriel, so we can follow to whom the questions are asking to. And now I will ask. I would like to give floor to Ricard García Valls. He's a PhD in chemistry by the Autonomous University of Barcelona. He was researcher at the Massachusetts Institute of Technology and lecturer at the Rovira and Virgili University, and currently he is the director of Chemical Technologies Unit at EURECAT. Ricard?
Thank you very much, Maria.
Sorry, this is a visual overview of the speakers today. Ricard, Francesca, Miriam, Pau, Gabriel, and myself. I'm in the middle, as you can see. Ricard, now the floor is yours.
Thank you. Can you show the next slide? Thank you very much. Well, first of all, thanks for inviting me. So, as director of the European Chemical Technology Unit of EURECAT, I'm very glad to be part of this webinar. I will try to coordinate a little bit the first part of the presentation. But first of all, I would like to give a short information about what is my unit, the unit I am directing, and also what is EURECAT. EURECAT is a technological center that has about 700 people working on it, with, scientists, innovators, and people working in more managing staff. From these 700 people, about 20 people are the ones working in the chemical technology unit, which is based in Tarragona. You can see the picture of the Roman amphitheater over there. Tarragona is famous for the tourism and also for being a UNESCO heritage for the Roman heritage that we have at the city. In the unit, within the unit, we have 4 strategic lines that are basically the ones that you can see on the screen. We have a strategic line on synthesis and catalytic methods. We have another strategic line on membrane technology and encapsulation. The third one would be in polymer chemistry and polymer technology. We are not a research center, we're an innovation center. And finally, we have the process development laboratory that tries to bring the basic lab developments to a level close to the pre-commercialization state. Can you show the next slide, please? So this was the, thank you very much, the short overview about the topic that we are going to start in 3 minutes, the photocatalytic synthesis call. That call was mainly, as all of you know, because all of you are interested in artificial photosynthesis, in the development of new processes. I like to say new, more than cheap, because cheap sometimes has could be misunderstanding, but the goal is to develop new processes that has more than 20% of efficiency, and that processes should take CO2 from different kind of sources. Could be atmosphere itself with direct capture, or could be from more concentrated streams, pipelines coming out of different kind of industries, and to convert that CO2 into valuable things that sometimes can be fuels, but sometimes could be other kind of chemicals that could start a new synthetic routes. The goal of the call was starting from TRL3 and reaching a point close to the TRL5. So it means we have to end up all the 3 projects, and I'm quite sure it's going to be a reality. We have to end up into small demonstrations that could be useful to guide companies and all the society to trust in this kind of processes and invest in them and make them a reality. So the challenge that the call has, and I think it's the challenge of all the scientists we already have, is to being able to demonstrate that and to initiate really a new kind of a chemical industry and a new, more green chemical economy. Okay. With that goal on mind, I would like to introduce the first speaker. She's Francesca Toma. Francesca is originally from Italy, and she got the master in the University of Padua. Padua, don't say Padua, Padua. And she has a PhD also in Italy, in Trieste. She got that PhD 12 years ago in 2009. And then 2 years later, she moved into the United States to the UC Berkeley. And nowadays, she's a staff scientist in the Joint Center for Artificial Photosynthesis of the Lawrence Berkeley National Lab. Apart from that, during these few years, but because she also only has 12 years since she is a PhD, she published more than 80 papers. And what is more relevant from all of that is that she recently got, a short time ago in 2021, an award from the American Chemical Society, saying that she's a rising star in chemistry. So I don't have anything else to say. I hope that you will enjoy and we learn a lot from all the speakers. And so now it's time for Francesca, please. Thank you very much.
Okay, thank you for the nice introduction, Ricard, and thank you for the invitation. I'm calling from California. I was discussing earlier. It's exactly 6:12 in the morning right now. Many of you may think that California is very sunny and hot. We do have a constant spring here, which makes it very nice living here. And this is a view of the San Francisco Golden Bridge. However, you may have heard or seen a few pictures last September of how California can also be. And this is a picture that was taken of San Francisco at 10 a.m. in the morning. It's so-called orange sky, and it's because in California we also have a fire season. I never would have think of living in a country with a fire season. Fire season here is becoming longer and longer, and the reason is because of climate change. So you certainly have heard of climate change and how it's correlated to the energy problem. We have carbon dioxide levels increasing and the global temperature is increasing, which is actually so what's causing the longer fire season. Arctic ice levels are going down, and ice sheets are also going down with an increasing sea levels. It's interesting to me how the Sustainable Development Goals of the United Nations are actually targeting all these issues, and specifically with a few goals. The first one being goal number 7 on affordable and renewable energies. And they ask us, scientists and in general, to collaborate and to enhance international collaboration in order to increase the share of renewable energy. And I'm glad to say that I'm collaborating with SunCoChem on trying to tackle these problems on renewable energy. So I said it earlier, and it might be counterintuitive on why the fire season is increasing if we have is becoming longer if we have temperature increasing, and the temperature on the planet needs to be looked as a whole and not just as a single point. And so having a constant increase may also involve having very cold winters and very cold summers that, as I said, are the cause for fires, flooding, and droughts over the whole world. So what is the solution? There have been proposed several different solutions that can take us to the path of zero emissions. Solar energy, wind energy, batteries, and solar fuels. And so I want to focus on some of these examples, and I also want to say that possibly the solution is not going to be made by just one of these technology. Solution is going to be made of a combination of all of these, and it will also depend on the type of applications that we are looking for, as well as where we are located to decide which one is going to be better. So if we look at solar energy and batteries, for example, we need to consider that the cost of solar power is decreasing, and in the past 20 years it decreased a lot, to make it possible to actually have a distribution or distributed solar power, residential solar power. However, it's also important that we keep in mind that these renewable energies needs to be stable, and specifically solar fuels and chemical fuels are a convenient way to store electricity, especially with respect to batteries, because of their gravimetric energy density. And you see it here in a graph which reports volumetric density with respect to energy density, gravimetric density, and lithium-ion batteries. So the existing type of batteries are down here, whereas you see that other fuels, biofuels, ethanol, and hydrogen specifically have all a higher content in energy. So Ricardo said it earlier, I work in one of I work in the Solar Fuel Hub in the United States. I was previously known as JCAP, Joint Center for Artificial Photosynthesis, which included 5 different institutions, Lawrence Berkeley National Lab, where I work, Caltech, UC San Diego, UC Irvine, and SLAC, and now this Joint Center for Artificial Photosynthesis has become the Liquid Sunlight Alliance, and also NRL, which is the National Renewable Energy Laboratory in Colorado, and Oregon University are also part of this coalition. Originally, at the start of the Joint Center for Artificial Photosynthesis, we focused on an integrated hydrogen generation, and now in the past 5+ years, we focused really on CO2 reduction and try to reduce carbon dioxide to fuels, to chemicals. This is just an example of what we are doing. I work from my collaborator Ian Sharp, who is now a professor at the Technical University of Munich, and this is a 3-5 semiconductor device that produces hydrogen. You're just going to see a video in a second where we shine light on this device and you'll see bubbles. So now the light goes off and these bubbles that you see are hydrogen. And this device has a efficiency of 11.3% solar to hydrogen efficiency. So I just show you this video to go a little bit backwards to show you what we are doing. So this 3-5 semiconductor device is a device that it's made of catalysts, it's made of light absorbers, and it's made of interfaces and contacts. And when we try to make an integrated solar fuel generator, we are looking at all these different components in the device. So my research at the Joint Center for Artificial Photosynthesis and the Liquid Design Alliance is really focused on designing interfaces for solar to chemical transformation, on characterizing these interfaces and materials with microscopy techniques based on atomic force microscopy and transmission electron microscopy. We also look at microenvironments to synthesize novel electrocatalysts for CO2 reduction, as well as looking at novel routes to reduce carbon dioxide via sunlight to solar fuels. So more into the energetics of what we are doing here, you can see the schematics of the device. We usually have an N-type photoanode, which is the light absorber that converts water into oxygen, and a P-type photocathodes, which it takes care of the reduction. And you can either make hydrogen from water or reduce carbon dioxide to fuels. And at the photoanode side, we have an upward band bending, and the photocathode side, we have a downward band bending with holes going on the surface of the photoanode and electrons going to the surface of the photocathode. The thermodynamic requirements specifically for water splitting is of 1.23 volt, and then if you add the kinetics of the semi-reduction and the semi-oxidation of water, that takes you up to 1.7 volt. These requirements are even higher, more than 2 volts for CO2 reduction. And these energy requirements are what we asked our semiconductors to do, to absorb light and convert that energy into an actual photovoltage that enable us to split water or to reduce carbon dioxide autonomously. So today I'm going to show you how we study semiconductors specifically and integrated photoelectrodes, and how we understand heterogeneity at the nanoscale. I'm going to show you an example of the mechanistic understanding of dynamic transformation in silicon gallium nitride photocathodes. And at the end of my presentation, I'm also going to show you how we do we tune selectivity by looking at microenvironments in CO2 reduction. So I show you some of the energetics of photoanodes. Bismuth vanadate is a photoanode that we use to oxidize water, and we develop a recipe for the synthesis of bismuth vanadate photoanode by reactive sputtering. So this is how bismuth vanadate appears at the nanoscale, and then we characterize this material by making a photoelectrode and by measuring CV curves or linear sweep voltammetry in this case. So you have a photocurrent measurement depending on the applied bias, and you can see here that the undoped, so without no molybdenum, the bismuth vanadate perform pretty badly, but then when you dope the material and you improve its properties, then you see a higher photocurrent and a better onset potential. So with sputtering specifically, we can make a scalable and reproducible synthesis, and with doping of materials, we can improve performance. But another very important point is how do we improve stability of materials. So specifically for bismuth vanadate, as well as many other materials, I have to say, it's very hard to have stability over time. So ideally, you would like your photocurrent density to be constant over time, but then when you put a material in an electrolyte, it's really hard to keep stability high. And here you see an example of the material just in a phosphate buffer at pH 6.8, and you see the current it's decreasing over time, and the situation is even worse when you have an alkaline pH. So if you look at scanning electron microscopy, you see here that the material as deposited has a very nice shape, a grain shape, but then the grains are kind of fusing together immediately after 60 minutes, pH 6.8, and the situation is becoming even worse after 20 minutes at pH 1.3. So we understood the chemical instability of this material with in situ characterization and also chemical characterizations, but here I report the in situ characterization that we did with electrochemical atomic force microscopy, which is this technique just schematically represented on the top corner. Here you have an atomic force microscope probe that is scanning on top of your surface, which you are biasing, and it's basically a tiny electrochemical cell where you're looking at the transformation of your materials over time. So here you're going to see a video of bismuth vanadate and how it's degrading over time, and you'll basically see the material dissolving and etching away. So from a very nice morphology, you see that the material is changing over time. So with this technique, we were able to see a real-time transformation of the material, and also understanding that the material degradation starts at solid liquid interfaces. This information, combined with other chemical information that we had, really told us that the material is degrading by dissolution, and we have ions of bismuth and vanadate that are going in solution. And this confirmed the original picture that I showed you earlier, which is that by SEM also we saw that the material was indeed degrading over time. So something else that we can do with atomic force microscopy is to look at the material at the nanoscale and try to provide more knowledge into the degradation of material and into how we can inform synthesis to make the material better. So in this case, we are using a laser, and we shine light from the bottom to our bismuth vanadate sample, and we also apply a bias on the bismuth vanadate sample. And then we can scan the tip on top of the surface, and we obtain this kind of maps that are topography maps with overlaid photocurrent. And in this case, we see that we have a photocurrent distribution that varies with respect on where you are on the sample. We have facet plane, facet boundaries, and grain boundaries, and we observe higher photocurrent distribution on the facet boundaries, which correlates, which tell us that we have defect tolerance in bismuth vanadate, since we don't have as much high photocurrent and grain boundaries, but also tells us about the heterogeneity of the photocurrent at a nanoscale, and we can correlate this heterogeneity with the macroscale performance of the material. This technique tells us about functionality at the nanoscale, but still we are missing the chemical information, which which we can obtain with scanning transmission X-ray microscopy. So scanning transmission X-ray microscopy is a technique that provides us with local chemical and electronic variation of material structure with a lateral resolution of about 20 nanometers. So we did this at the advanced light source. We also got help from David Prendergast at the Molecular Foundry to interpret some of the spectra that we obtain at the beamline. And these are the type of results that you obtain at the STXM beamline. We looked at the vanadium edge and the oxygen edge, and we look at differences within the sample, and we could recognize two main regions. One is the grain center, and the other region are the grain edges. And specifically at the grain edges, we did see more vanadium oxide, which if you correlate to the degradation that I showed you earlier, the solid-liquid interfaces can tell you more about what might be going on when you degrade the material. So this presence of vanadium oxide might increase the probability of degradation of the material. In the second part of my talk, I'm going to show you how we provided mechanistic understanding of transformation in silicon gallium nitride photocathodes. So we collaborated in this case with University of Michigan, Zeti and me, specifically at University of Michigan, who found that silicon gallium nitride platinum photocathodes are really stable and efficient for hydrogen production. So we wanted to understand more what was going on with this stability and what was the mechanism for long-term stability. So we just looked at the silicon gallium nitride photocathode specifically, and we started looking at linear strip voltammetry over time and also chronoamperometry to look at the decay or the constant current over time. So what you can see here is the self-improving behavior that we observe, in which from the beginning, so it's this red curve, you see the onset potential becoming more anodic. So basically the potential at which hydrogen production starts is anticipated, and you also see an increase in the photocurrent density. So by mapping the chemistry as a function of time, and here at the bottom you have a chronoamperometry, so current as a function of time, you see that at the very beginning in the pristine material, looking at the oxygen 1s in the X-ray photoelectron spectroscopy, you have an oxygen peak related to the oxygen bound to gallium oxide, and the hydroxyls related to absorbed water. And then as you start biasing the sample, you see this increase in the photocurrent, and you start seeing a new peak that appears, which is a peak that it's related to oxynitride, gallium oxynitride. The component becomes even stronger as you keep biasing the sample, and it becomes constant after about 10 hours. This increase is related to an increase that we observe with the transmission, scanning transmission electron microscopy. You see here the gallium, the grains of the gallium nitrides, and the map of the elements with EDX. So you have in blue oxygen, yellow gallium, and green nitrogen. This is the pristine sample, and then after the test, you see here that you have an increase in the oxygen concentration, both on top of the grains, but what's most important here, you see that you have an increase in oxygen concentration at the sidewall, which is also accompanied, is colocalized with the presence of nitrogen. And instead, on top of the grain, you don't have this nitrogen component. So this confirms you that you are forming oxygen nitride, oxynitride, gallium oxynitride at the sidewall of the grain. And we know that the higher photocurrent might be coming from the sidewall also because we did photoconductive atomic force microscopy, and we observed higher photocurrent as you can see here, coming exactly from the sidewall of the material. So by DFT calculation, we looked at the formation energy of the oxynitride specifically, and we found that on the polar plane, which is the sidewall of the gallium nitride, the most stable phase is the partially oxygen substituted one. And in addition to that, we also know that this surface is also the more optimal for the absorption of hydrogen. So we basically know that this phase, this substituted oxygen gallium nitride phase provides us with more catalytic sites for hydrogen production. And here is a long-term stability test performed at high illumination 3.5 sun for 150 hours. So this material is stable and can also make hydrogen with high Faraday efficiency. In the last part of my talk, I'm going to show you how we look at nanointerfaces and microenvironments to tune CO2, the selectivity in CO2 reduction. CO2 reduction is a really challenging reaction because it can give you up to 16 different products, specifically on copper surfaces. And controlling the selectivity and the efficiency of this reaction is really challenging. So what we can do is taking inspiration from nature, and nature, of course, reduces carbon dioxide to the process of natural photosynthesis. Natural photosynthesis, we have an enzyme called rubisco, which has a magnesium atom specifically, and this enzyme is responsible for CO2 fixation in plants. There is this catalytic pocket, as I was mentioning earlier, that can capture and then transform CO2 reduction. So the question is, how do we take inspiration from nature, and how can we make local environments that are able to selectively transform carbon dioxide into products? We looked at literature, and we looked at how we can modify surfaces in a controlled way so that we can tune selectivity. And specifically, we took copper foil, and we turn this copper foil into an oxide-derived copper, which is known to be more active for CO2 reduction. And then we functionalize copper with different polymers and molecules that had structural parameters to try to tune CO2 reduction in a controlled way. So specifically, what we tune in these structures, and you see them here, we utilize ammonium salts and polymers like polyvinyl pyrrolidone and polystyrene, polyvinyl alcohol, among others. And you can see that what we are varying here is the hydrophobicity and hydrophilicity of the structure. And specifically, we can characterize these molecules by different hydrophobicity and hydrophilicity. And what we observe is that more hydrophilic surfaces will give you more formic acid, and more hydrophobic surfaces will give you more CO. And this is in agreement with the water density at close to the electrode surface. We did this in collaboration with Bill Goddard and Tao Chang, and these are DFT calculations that looked at the water density close to the surface. And what you can see here is that indeed a more hydrophilic molecule will have more water and a more hydrophobic molecule will have less water. And this content of water is correlated with the energetics of the reactions that gives you either formic acid or CO. And what you can see here in this diagram is that more hydrophilic surfaces are more prone to energetically more prone to produce formic acid. So formic acid production is basically favored on hydrophilic surfaces with respect to hydrophobic surfaces. So in summary, I show you how we look at heterogeneity at the nanoscale and how this is correlated to macroscale performance and stability. I show you how we characterize the silicon gallium nitride photoelectrodes and how we observe this self-improving mechanism on gallium nitride, and how we can tune local environments and specifically the role of hydrophobicity and hydrophilicity in CO2 reduction. I want to acknowledge all my collaborators, specifically for the bismuth vanadate project, Ian Sharp, Jason Cooper, and Sebastian Reyes Freeland and Joel Ego. For the gallium nitride work, Zetian Mi, Tadashi Ojitsu, Anfen, Jason Cooper, and Srinivas Vanka, and for the CO2 reduction project, Tintos, Pilkoden, and Tao Cheng. And I want to say that none of this work would be possible without the great team that worked with me, specifically the work on bismuth vanadate needs credit by Johanna Haykorn. The work on gallium nitride was performed by Guo Song Zhang, and the work on selectivity in CO2 reduction by Aya Buckley. And I'm open to any question.
Thank you very much, Francesca. Can you hear me now?
Yes.
Very interesting, interesting presentation. I didn't receive any question via the chat over there, so I will start having the question myself. The first is a curiosity. When you presented the video you obtained with the AFM, the time scale I could see like it was minutes. You were talking about you were seeing the transformation with minutes, and you're taking sort of pictures for 60 seconds, 80 seconds, 120 minutes. Sorry, I mean, yeah.
Yeah. So the let's say the resolution, the time resolution that we have, it's in order of minutes, and it's depending on the scan rate of the AFM. Of course, the faster you go, the lower the resolution that you have. There are techniques with AFM that allows you to get fast imaging. We haven't tried those specifically, but it's something that one can think of to put together these type of measurements with the fast scanning in AFM.
In fact, that was my curiosity, because as far as I know, we do AFM as well, and it takes some time to get all the scanning all the surface, because the tip goes traveling up and down, and so
yes,
that's a limiting step in having more continuous pictures, right?
Yes, totally. And you know, there are ways that you can overcome this issue, specifically like circular, like by a circle, instead of scanning like line by line, you can scan circularly, and then you can integrate the image, and then would give you more resolution and faster imaging too.
Mm-hmm. Interesting. Yeah. I keep asking myself, I don't see any more question. People in chat, sometimes it's difficult to get, oh, I see a question. Yeah. Okay, I can read the question for you. There's a question saying, it's coming from Matthew Mayer. And the question says, you mentioned the gallium oxynitrate phase is more catalytically active for hydrogen evolution reaction from correlation of the local current density. Can you say more about this? Is there a hypothesis active site responsible for HER?
So the way by which we looked at increased catalytic sites was by calculating hydrogen adsorption on different phases of gallium oxynitride. So basically, we did see that the free energy for hydrogen absorption was optimized on the gallium oxynitride phases. So that's and specifically substituted at 50%. So that's how we performed that type of calculation and how we arrived at this conclusion. We are currently doing more analysis, specifically by ambient pressure X-ray photoelectron spectroscopy, to understand better about the energetics and to understand more about the presence of these catalytic sites. So more will be coming, basically. I still don't exactly know experimentally how this is working, and the information that we have is more based on prediction that that basically tell us that the free energy of hydrogen absorption is lower on the gallium oxynitride.
Okay. Let me see, there is no more question. I had another question myself, because we also work producing formic acid by CO2 reduction by electrocatalysis in our case. Did you choose formic acid because of the thermodynamical advantage? Of course, it's the first one that comes when you're transforming CO2, or do you see that there is a target component in the future as well itself? Do you see it?
Yeah, we chose, basically, we wanted to focus on a potential region where you had just 3 products, or the minimum that you could make on copper. So we looked at how you can vary the selectivity between hydrogen, CO, and formic acid, with the idea that, of course, if you can optimize the selectivity towards CO, then you can go down the scale towards higher hydrocarbons. When we started this study, the promise for formic acid in the field was actually not as good, but now there are quite a few papers that also look at what you can make basically with formic acid, and formic acid fuel cell as well seems to be another application. So it looks like there is some promise for formic acid as well, and it can be a good product that you can make by CO2 reduction beyond other higher hydrocarbons as well.
Completely agree. Yeah, we got some more questions here. There's one coming from Roberto Gonzalez. He's saying, AFM studies show the degradation of the bismuth vanadate sample. Way about the crystalline structure. Okay, what about the crystalline structure? Is typing in here.
Yes, so our samples are polycrystalline. We do not look at single crystal structures. It is an interesting question because stability could depend on facets, and also could depend on surface termination. There is a very nice work from Kyung-Shin Choi and collaborators from Madison, Wisconsin, where they show that depending on your surface termination, then your stability and also performance of the photoelectrode can change. In our case, it seems that we also have more bismuth at the surface, with, according to Professor Choi's study, seems to bring higher efficiency, but yet we still see the material degrading. I think that an important point when we look at this type of materials is considering kinetics versus thermodynamics. So the material might be very good at giving you charges to actually oxidize water, and if you have a sacrificial reagent that can efficiently extract these charges, then you're okay. But then a lot of the studies that we do are actually without sacrificial reagents, so you're really looking at the material under operating conditions, how it would oxidize water in this specific case. And we see that there is a kinetic barrier for the charges to actually go and oxidize water, rather than recombine and oxidize the material itself.
Okay. A few more questions came to the chat now. We still have 5 minutes to go. One from Ponar Aaron Rats Meruang. Sorry for the bad pronunciation of your name. It's saying, can gallium oxynitrate be prepared by solution process?
Yes, great question. We have now looked into solution process. We are looking at atomic layer deposition. The way that we deposited it, that my collaborator deposited it, is MBE growth. So it's a very high quality gallium nitride, and really the next step is trying to see how a less high quality gallium nitride would perform, and if we can reproduce the type of stability and the type of mechanism on, let's say, an ALD, atomic layer deposition deposited gallium nitride.
Okay, another one coming from Habibullah. He's saying just a formal question, how the DFT was performed, supercomputer or Material Studio?
Good question. We didn't use a supercomputer. The calculation was performed by our collaborators, and yes, now I don't remember exactly the details, but I would say that they used Quantum Espresso to perform their calculation.
Okay. The next one is saying from.
Let me say that
yes.
if they are interested in the details for the calculations, they are reported in the supplementary information of our paper, which is Nature Materials that was published at the beginning of this month.
Wonderful. Yeah. Okay. The next question coming from Kumarabel Dinesh is saying the loss of vanadium led the catalyst decomposition to the bismuth employed by the CO2 reduction. How could it be rectified?
Can you repeat? Sorry.
Yeah, the loss of vanadium led to catalyst decomposition when the bismuth compound employed in CO2 reduction. When I suppose that there is missing some word here. How could it be rectified and corrected?
Yes. We can. There are different ways. Again, there is an interesting study from the Choi group that shows that if you have vanadium in solution, you can actually basically, because of the Chatelier principle, you can push the equilibrium in the other direction, and basically you can preserve vanadium loss from the electrode, which is quite interesting as an approach. More conventional ways to protect materials are by deposition of lower layers, and we did look at how you can passivate bismuth vanadate surface in a way that you still make it active, but at the same way you can protect it. And we looked specifically at overlayers of cerium oxide combined with iron oxide and nickel oxide as well. So those are ways in which you can prevent. So it's basically a physical barrier that that you can put in addition to a barrier that ensure a better charge extraction at the interface. So it's basically what I mentioned before about having something in solution that is able to efficiently utilize charges. You can also make a better interface between the photoelectrode and the solution by utilizing an overlayer, and that overlayer allows you to extract charges more efficiently and to transfer those to the solution. So that is another way to protect the material, and it's an efficient way to do that.
Okay, thank you very much. I'm afraid that we ran out of time. It was an interesting discussion, and thanks for a wonderful presentation, Francesca. I mean, we get more questions on the application. We will send these questions to you, and will be answered by email by the organization. Okay, thank you very much, Francesca.
Thank you again.
Okay, and now I give the floor to Maria again.
Yes, hello. So I guess now the presentation must be shared by Miriam. Okay. Next session is for the present. Yes, here we go. So I will give a brief introduction About Miriam Diaz, yes, the whole curriculum vitae of all the speakers you can find in the program, so I will just go in to be brief. Miriam Diaz is a PhD in organic synthesis from the Rovira i Virgili University in Tarragona. Currently, she is the head of the synthesis and catalysis line at the EURECAT Chemical Technological Unit. And she is the scientific coordinator of SunCoChem, which she is going to present. The floor is yours, Miriam.
Thank you, Maria, for your introduction. Can you see my screen, my full screen?
Yes, yes.
Okay, thanks, Maria, for your introduction. First of all, I would like to thank all the participants for joining this symposium that we have organized in the framework of this first anniversary of the project SunCoChem. My name is Miriam Diaz de los Bernardos, as Maria said, and I belong to the Unit of Chemical Technologies in EURECAT in Spain. And I want to present SunCoChem, which title is Photocatalytic Device for Sun-Driven CO2 Conversion into green chemicals. Before starting with the technical part, I would like to say that we have a very collaborative consortium. As you can see, our consortium is very big. It's formed with 14 partners from 8 different European countries. And I would like to thank all the members of the projects because they have been joining the project since the very first beginning, and they have been working very hard and in a very collaborative manner during this first year of the project for making this idea possible and to finally obtain a very good solution. So SunCoChem is conceived in the SunCoChem is conceived in light of the most important challenge that the European chemical industry is facing nowadays, which is the transition towards a low emission industry. Currently, the European chemical industry strongly depends on the carbon fixed materials in both for energy imports and as well for chemical-based manufacturing processes, which over 95% of them depends on fossil fuels. That leaves the chemical industry as the third largest greenhouse emitter in Europe, with over 30 gigatons of CO2 emitted per year. In this context, which is the technology that SunCoChem pretends to develop to help a bit to decrease this strongly depends on carbon feedstock. Well, SunCoChem pretends to develop a photoelectrocatalytic device. I represent this device as this green box here. And this is going to be a self-sufficient device, which are going to combine different technologies in a single unit. And we are going to start using as raw materials very abundant compounds such as sunlight, water, and CO2. That this CO2 is going to be captured directly from a Dow company that we have here in Tarragona, which is where they do a process for the production of ethylene. So, which are going to be the transformations that are going to take place inside this device. First, the sunlight is going to be harvested, and those photons are going to be converted into chemicals by a sun-driven process. So once the sun is going to be absorbed, it will induce a transformation of water. The water is going to be oxidized to produce molecular oxygen. Also, are going to release some protons and electrons that are going to react towards CO2 with recycled CO2 from Dow to produce carbon monoxide. And this carbon monoxide is going to be used as a precursor for a tandem process, which is going to be a non-photoassisted tandem process, hydroformylation reaction, to produce 3 oxo products that are actually being manufactured in large scale for different important chemical companies such as IFF and Dow. So in the end, SunCoChem pretends to develop an artificial lift type device that will mimic natural photosynthesis for solar harvesting, the CO2 capture and conversion to organic chemicals. As I say, different oxo products are going to be produced by our technology. Those oxo products are actually being produced in larger scale with technologies that depends on fossil fuels. Glycolic acid is going to be produced by the formulation of formaldehyde using the carbon monoxide and hydrogen produced renewable by water and sunlight and the captured CO2. And this glycolic acid has a wide variety of applications. For instance, they can use as flavoring and preservative and emulsion additive. Also, valeraldehyde is going to be produced by the hydroformylation of butene. Here it's important to note that this butene is going to be provided by Dow, also by the same company here in Tarragona, because butene is one of the byproducts that they are obtaining actually in its process of steam cracking for the production of ethylene. So valeraldehyde, it's also nowadays manufactured by Dow in larger scale, and with SunCoChem technology, they can produce valeraldehyde by just mixing two of their waste, butene and CO2, and with a sun-driven process. Valeraldehyde, it's also applied in different markets as food flavoring, in resin and rubber products. Finally, limoxal is going to be produced by our technology, also by the formulation of limonene. Limoxal is actually manufactured in large scale by the company of IFF, which is a company specialized in flavors and fragrances, and they apply this building block as a perfuming agents in personal care and house cleaning products. Okay, so in the end, for large scale organic production, utilizing a sun-driven processes, there are a lot of scientific challenges that we need to address. The coal requirements needs an overall solar to chemical conversion efficiency up to 10%, and those are the targets that we propose for achieving these values of efficiency in terms of selectivity, product efficiency for CO2 production, current density, quantum efficiency, the overall potential required, and the oxo product yield and selectivity. So if to obtain those targets that we fix in the proposal to attain the requirements of the call, it's necessary the development of different materials. One of the more important are the electrocatalysts, the electrodes that we are going to develop to achieve such values of efficiency in our device. So SunCoChem plans to develop multi-heterojunction photoelectrode materials for Z-chip mimicking. Our photoelectrodes are going to be composed by cheap and earth-abundant metal oxide nanoparticles that are going to be used as semiconductors, and are going to be actually are being developing Laurentia. EURECAT is also developing molecular organometallic chromophores that are going to be used as light harvesting, and molecular catalysts that are going to be conmobilized with those light harvesting agents in the surface of the semiconductors for each process, okay, for the three transformations that are going to take place in the single device: the water splitting, the CO2 reduction reaction, and the hydroformylation process. Another important material that needs to be developed in this project and that plays a special role, an important role, is the development of ionic liquids. Iolitech is the company in charge of the development of those ionic liquids. And those companies are particularly important in SunCoChem, because in the end, what we pretend to do is to develop a technology for larger scale organic synthesis. And one of the main drawbacks that the industry is facing nowadays for large-scale organic synthesis using electrochemical based technologies is the poor solubility of the organic reagents in the aqueous electrolytes that are actually using for electrochemical processes. So by the use of by the development of ionic liquids, we can tune the solubility of the electrolyte. We can develop novel cations and ions of ionic liquids that and to obtain the desired solubility for increase the solubility and the concentration of CO2 and the organic reagents that we need for our hydroformylation process. So increasing these concentrations, we are going to increase, we pretend to increase also diffusion rates, okay, and of course to increase, that will increase the production rate. Besides, the ionic liquids possess better physical sorption, lower viscosity, and in terms of long-term stability, they have very good electrochemical stability windows. So that means that over several hours of running, the electrolytes could remain stable. So that for stability issues, it's a very good point as well. Another key material that should be developed, that we are already start developing in SunCoChem, is a transparent bipolar membrane where our electrodes are going to be assembled. And this technology will help to achieve our efficiency, because with these membranes we can maintain constant pH and ionic gradients at both the anode and cathode compartments, and we can use different electrolytes. So we can, in each part of the device where its transformation is going to take place, we can have their own catalytic systems to maximize the catalyst performance. Another requirement that the call says was to obtain a device, to develop a technology that maintain its performance, okay, that doesn't lose much more than 5% of its performance after 1,000 hours running. Also, we need to develop a device that with a cost reduction up to 30% compared with the actual technologies based on fossil fuels. And we need to reduce the CO2 emissions comparison with actual routes for the production of oxo products up to 50%. So the key points towards the cost reduction and the stability of our device, I think it's the device engineering, because we are gonna develop different technologies, and we are gonna build a single device. So all the components are going to be integrated in a single device. Our device will have another chamber, will integrate anodic chamber for water oxidation, a cathodic chamber for CO2 photoelectrode reduction, and also the non-photosynthetic process, which is the either formulation reactor for the corresponding oxo products. In this cathodic chamber, ionic liquids are going to be used as electrolytes, and we are going to use a transparent bipolar membrane for assembling those electrodes. Also, the technology of the CO2 capture and conversion of the CO2 capture is going to be integrated in the device, where the CO2 is going to be captured from the gas stream from Dow company using an asymmetrical isoform membrane, which is going to be also developed here in EURECAD. And in this chamber, ionic liquids are going to be used as well for, as I said, concentration of the CO2. There is another partner also, that Solaronic, that will develop low-cost perovskite solar cell to boost the internal photovoltage of the device and obtain these values of efficiency and stability that the code requires. Well, SunCoChem is thinking of 4 major, will be developed in 4 major phases. We have to go from TRL 3 to TRL 4. The first phase is the development of material and components of the tandem photoelectrocatalytic reactor. We are actually in this part of the project. We have been working for 1 year already. And the second phase of the project is upscaling, testing, and validation of the tandem photoelectrocatalytic reactor. Here is where we're going to start at TRL 3. We're going to have the experimental proof of concept. Then the third phase is going to be the integration and optimization of the materials and companies, where we are going to achieve TRL 4. The technology is going to be validated in a lab scale. And the fourth phase, which is going to take place all over the project during the 48 months, a socioeconomic and environmental impact assessment will be done during all the project, as I said. And finally, to achieve this TRL 5, in our consortium, we have a lot of partners that they have very strong experience in the design of this kind of artificial lift type device, from going from lab to pilot scale. So this will be exploited as our starting point for the design of our prototype and achieve this validation and achieve this prototype, and it's going to be validated in an industrial environment at IFF for the conversion of the CO2 recycled from Dow to the oxo product that they are commercializing, the Limoxal, using the sunlight that they have in the plant of IFF that is located in Benicarlo. So that's all from my side. Thank you very much again for your attention and for attendance in this symposium. And of course, I'm open to any questions.
Thank you very much, Miriam. Very nice presentation. Now it's the turn of Pau Farras. Be ready for your moment. So Pau is a PhD in chemistry from the Materials Science Institute of Barcelona. He is an active member of Hydrogen Europe Research, and he is the coordinator of 3 European funded projects, Solar2Chem and C-Fuel, and of course Flow Photochem, which is the project he's going to present now. He's at the moment lecturer at the National University of Ireland, Galway. Pau, the floor is all yours.
Thank you, Maria, for the introduction. Can you confirm that you can see my slides full screen?
We can see perfectly, yes.
Very good. So thank you, first of all, for the invitation to give me the opportunity to present the project that we started about 1 year ago, more or less, which is this Flow Photochem project, or like in the longer title, Heterogeneous Photoelectrocatalysis in Flow using concentrated light. So I just don't want to give much more background that my colleagues have already done. But basically what I wanted to share is that, in fact, the European chemical industry is one of the biggest industries in Europe, which gives like a huge amount for revenue, about 500 billion sales, and also direct jobs of about 1 million people. The problem, of course, is that it is also a high polluting industry, and we need to find ways to try to reduce these issues. And of course, this is directly related to the European climate targets for CO2 reduction, and basically to achieve the climate neutrality by 2050. So basically, in the project, we are looking at these 3 main sustainable development goals, as Francesca has mentioned before. And in our case, we are focusing on the affordable and clean energy by producing clean fuels, green fuels, the responsible consumption and production by producing green chemicals, and also, of course, the climate change by developing technologies that we consider are carbon negative. This is also seen by basically the CO2 emissions that the chemical industry are releasing. And if you look at the global CO2 emissions from the industry, most of the industries that are like really highly emitters for CO2 are related to the production of high value chemicals, or even the precursors for the chemical industry that we need to produce, from plastics to all the other things that we are using in our everyday lives. So when we talk about the chemical industries, we have this graph that was, I basically took it from BASF, which basically relates the potential of CO2 reduction with the costs and risks that are associated with these steps. Yeah, so of course we can go from optimizing the energy processes in the chemical industry, and this will achieve until a point. But of course, if you are aiming to achieve the targets for 2050 for climate neutrality, we really cannot get stuck into this first point. Then the next step would be, of course, to couple these processes with renewable energies, and this can help to mitigate some examples, like for example on the cement industry by using green hydrogen to reduce the amount of CO2 emissions. But again, this will be only cover part of the chemical industries that we are targeting. Last one is basically to go through the breakthrough technologies, and that's basically where the Flow Photochem project is looking at. So developing technologies that are capturing CO2 and using that to produce the chemicals that we are basically getting now coming from fossil fuels. And very recently, just a couple of weeks ago, there was this nice paper that was published in One Earth that was basically comparing the type of chemicals that can be produced from renewable, let's say, sources compared to the actual production that is coming from the fossil fuel-based petrochemical industry. And we can see here that there are many of these chemicals that are actually already currently available that you can produce directly from CO2 and renewable energy sources. So there are some of these complexes, like, for example, the production of methanol, which can be used producing using green hydrogen and CO2 in a CO2 hydrogenation plant. And there are examples of this, for example, in Iceland, which they are producing already tons of methanol using these renewable routes. So our ambition is basically to look at some other of these products and see how negative CO2 emission technologies can help to achieve these same precursors for the chemical industry that are relevant and basically displace the use of the fossil fuel-based solutions that we have now. So the project aim in particular is to design, develop, and translate to market new materials. These include photoabsorbers, catalysts, and membranes, and also the flow reactors, which can use solar energy, water, and CO2 to produce a variety of fuels and chemicals. And these are basically either hydrogen, ethylene, syngas, etc., etc., etc. Okay, so the idea of the project is to produce a modular design, a modular system, which allows us to basically, through 3 different types of reactors, a photoelectrochemical reactor, a photocatalytic reactor, and an electrochemical reactor, to produce a wide range of different products that basically can displace the ones that we are getting now from the fossil fuel petrochemical industry. Yeah, so basically, this will be the overall scheme. And to achieve that, we will be looking at these 3 different types of reactors and the integration of these type of reactors. Of course, we cannot do everything. And in particular, as Ricard mentioned when he was looking at the call text, you need to demonstrate the technology at Tier 5. So we need to focus on some product. And we did that by looking at ethylene. Okay, so the vision of the project is a process like this. So it would be this integrated modular system, which combines the 3 reactors in a combined system, in which we are using concentrated light, okay, to drive the formation of hydrogen, green hydrogen from water in the first reactor. In the photocatalytic reactor, we will be also using solar energy to drive this reaction. And by combining the hydrogen from the first reactor and CO2, we will be targeting the production of carbon monoxide. This carbon monoxide can be then injected into an electrochemical reactor that, combining with water, will be able to produce the ethylene. The idea of the overall system, the modular system, is to achieve an efficiency of above 7% sunlight to chemical conversion, in particular like the conversion to ethylene, and also with a performance loss of less than 5% over 1,000 hours. Also, we will be looking at lowering the cost compared to the fossil fuels, and with the aim to achieve this vision for Europe to achieve the climate neutral society by 2050. So why do we choose ethylene as our chemical target? Because if we look at the different types of chemicals that we can produce from CO2 and water, we see that in particular ethylene is the one that has the highest value. So that's about $1.3 per kilogram, more or less. And also is one of the highest in terms of market, since ethylene is one of the biggest precursors for the plastics industry. So how are we going to deliver this modular approach? So we have these 3 different work packages looking at the 3 types of reactors. And a 4th work package will be the integration of all these. And within each of the reactors, we have basically the same approach in which we are starting from modeling guidance in terms of designing the best materials, the best catalyst. Then, of course, we will prepare and test this catalyst. For the solar-driven reactors, we have to do the integration, either in the photoelectrode or in the photocatalyst. And, of course, then the design of the flow reactor itself. This is combined with the sustainability analysis. So we are taking care of the environmental impact on each step of the process. So from the type of reactor, the type of materials that we're using, to the design of the reactors, and of course then looking at the exploitation of the results that we will be getting from the project. And the aim of the project is not basically to look at how we can produce ethylene using this process, but in particular how we can develop these different families of reactors and integrate them in order to fabricate the components, the photoabsorbers, the catalysts, and the reactors that will allow not only to produce ethylene, but also all the other products that we are aiming at. So these are some of the configurations, and that's why it is important for us to look at the 3 different reactors that we are looking at now, because the different configurations that we have envisaged to produce ethylene are these ones. Okay, so right now, with the current status of the technology, we believe that option A is the most feasible, which is basically producing hydrogen with the photoelectrochemical reactor, hydrogenation to CO, and then the electrochemical reactor to produce ethylene. But also there are 2 other options. One is you use the same photoelectrochemical reactor for hydrogen, and then the photocatalytic reactor would allow also the CO2 hydrogenation directly to ethylene. On the other side, we have also a photoelectrochemical reactor that is not anymore now producing hydrogen, but also we are doing the CO2 reduction on the cathodic side. So we will be producing CO in the first reactor, and this CO can be fed directly into the electrochemical reactor to produce ethylene. So in order to achieve the target efficiencies, the solar to chemical efficiencies, these are the type of individual reactor efficiencies that we'll be looking at. The implementation will follow these steps. So of course, we're starting in the first year with the concept and the optimization of the materials. And after 4 years, we expect to have this system model that will allow us to start the next step of commercialization. These are the different steps that we are looking at. Okay, so from the materials to the characterization to the reactor design and construction. But we have also the modeling steps that are very important for us, because this will allow us to integrate the 3 different types of reactors into a fully integrated system and a standalone system that will allow the production of these different chemicals. So where we start with? So in the first case, the photoelectrochemical reactor, we are starting with this reactor that was developed by our partner EPFL. And what we see here is basically the solar concentrator, in which you have then the photoelectrochemical cell in the focal point. And the current reactor is able to produce already about 800 milligrams per hour of hydrogen. Our aim to achieve the 500 kilos of ethylene per year is that we should have a reactor like this that is producing about 10 times this amount. So that's one of the first challenges, the reactor scale up, but also the other challenges that we are facing for this reactor are the reducing the amount of precious group metals, both in terms of like the reactor, the catalyst that we're using in this baric junction photoelectrochemical system, but also on the photo-absorbing materials. Then, of course, it is important to improve the performance of the membranes that we have in these systems. So the membrane that is used in this photochemical reactor is an Nafion based, and it allows only to work up to about 70 degrees. So we are developing membranes that allow us to work at even higher temperatures, which in principle would allow the increase of the production rates for ethanol, for hydrogen, but also to see how we can integrate the reduction of CO2 in this first photoelectrochemical reactor. In the case of the photocatalytic reactor, our starting point is this reactor developed at the University of Valencia. And in that case, as Francesca mentioned, one of the challenges in this reaction is really the selectivity to achieve the desired compound. If we are aiming for CO, we have to play with the temperature and the pressure. And this has some direct effects on the design of the reactor. And that's one of the things that we are working now on, designing reactors that allow the operation at higher temperatures and pressures. And the challenges that we are facing is the selectivity towards producing solely carbon monoxide, but also trying to reduce the operating temperature and pressure while achieving the same production rates for carbon monoxide. And of course, the matter of the reaction scale. Since for this reactor, our target is the production of about 63 grams per hour of carbon monoxide. The last reactor is the electrochemical system. And we are basing our reactor designs based on the CO2 electrolyzer that is being developed by our partners in the University of Szeged. This work package is led by our partners in Helmholtz, Berlin. And we are basically targeting different types of materials and also membranes in order to have the selectivity towards ethylene. So in this paper that was published also a few weeks ago, there is this comparison of CO2 electrolysis to ethylene. And as we can see here, there are quite a difference between the optimistic values that we are sort of trying as a target compared to the actual data that we have now. And we see here the cell voltage that is required for this reaction, but in particular also the Faraday efficiency and the electrical efficiency that we have for this. But of course, for the fact of the scale up that we need to achieve the target values that we are achieving. Okay, so the challenges that we are working on this electrochemical reactor are, of course, not only the scale up, but also to improve the selectivity. And this is related to developing new materials for the cathodic side, for the CO reduction to ethylene, but also developing new materials for the anodic side so that we can also reduce the cell voltage that is required to drive these reactions. And of course, improve the performance of the membranes that are actually currently used now to avoid issues related to the formation of carbonates that is known that is happening for the CO2 reduction, which in principle should be allowed, not impedance for the CO reduction. So the integration of this will be done in work package 4, and also in work package 1 to 4, we are looking at this multi-physics, multi-scale modeling of the reactors. So we have the aim, the target to basically try to couple the atomistic simulations of studying the electrocatalyst and the photocatalyst that we are developing in the project. Couple this with really the Monte Carlo simulations on the reactor scale. Couple this with the whole process and plant simulation that we will have for the integrated system. So the final integrated system will be tested at DLR's facilities, and we will have two different types of testing conditions. One in continuous testing, and a second one that will be basically in on and off cycles that would be in this stress test that will have basically to prove the stability of the whole system for this 1,000-hour period that we are aiming at. So for the route to market, we'll have also, of course, this sustainability analysis and also the market analysis for the exploitation. And basically linked to this, we have in our partnership, we have also a group in Africa, in the University of Kiambogo in Uganda, which basically will allow us to exploit also the technologies in African countries. And basically, we have also two workshops scheduled in Uganda to basically explain the technology that we will be developing. So in this slide, you can see basically all the partnerships. So we have 14 partners across 8 different countries, with partners working on catalyst design, manufacture, and characterization, the modeling of the catalysts, the modeling of the reactors, and also the demonstrators, the exploitation and commercialization with our industrial partners, Thales Nano, Johnson Matthey, and Member Sense, the life cycle analysis and sustainability with NY Galway and like that. And of course, most important also is the communication and dissemination that Pintel is in charge of. And with that, I will like to finish showing, unfortunately, one of the virtual project meetings that we have had in the project. We hope that soon enough we'll be able to do our next meeting in person, and we can show you a group picture of the more than 30 members that are working on the project. And also my group in Galway, which I would like to highlight, Simon and Hanka, which are the ones that are responsible for the work, our contributions in the Flow Photochem project. And with this, I'd like to finish, and thank you for listening, and happy to answer any questions. Thank you.
Thank you very much, Pau. Yes, I think there was already a question for you, so but this will come after Gabriel's presentation, as I explained earlier. So Gabriel, be preparing your presentation because you are the next one. I will introduce Gabriel briefly because his curriculum is really extensive. Gabriel has been a coordinator of the European Network of Excellence, IDCAT. He is the president of the International Association of Catalysis Societies. He has been coordinating or as a principal investigator in around 20 European projects. He's also part of the board of SunEnergy, the European Initiative on Solar Fuels. He's at the moment a full professor in the University of Messina and also the president of the European Research Institute, ERIC. So, Gabriel, I don't know, we cannot see you because I don't know if you have the camera off, but in any case, the floor is yours.
If it's working now?
No, I cannot see.
Now?
Yes. Now, yes, now.
Okay, and I don't know if you see my presentation.
Yes, we see it. Thank you.
Okay, many thanks. So good morning to, or good afternoon to all, and thanks for this opportunity to share some of the concepts that we was trying to develop within DECAD project. I like also to very briefly to introduce a few words about some of the vision of SunEnergy, which is, as mentioned, this large initiative that we are pushing at the European level on solar fuel. And I believe that this kind of meeting in which there are different kind of projects around this concept is an excellent example of the direction in which we need to go, because it's clearly that to really change the future and to go to really to transform the actual production of chemistry and energy, we need to share all the information. So DECAD project is let me say, a kind of a new approach in photoelectrocatalysis for the conversion of carbon dioxide. But before to start on this, I like to say a few words about some of the vision aspect on SunEnergy. What are the direction, because this is part of the general objective also for DECAD projects. I think that the challenge that we have, and if you like to have more information, you see a reference here on a paper on catalysis review. The The challenge that we have is really to go or beyond the linear model that we have today in converting carbon dioxide, in converting fossil fuel into produce carbon dioxide, in which more or less we have we put on the atmosphere or we haven't captured. What we need clearly is to go to the future, to go to a kind of circular model, a circular economy. And we can see that this can be made in two steps. One, first steps in which we have a kind of indirect circular model. And in this case are very important all the technology that we have in terms of carbon utilization, essentially by thermochemical process today, while in more a bit more longer term, but what I see is not very far long term. I see a target in 10 years, so around 2030, where we go to a real direct and full circular economy, or at least we start to go in this direction. And clearly, if we go in this direction, all the aspects central are all the electrocatalytic process and all aspects related to a refinery and also artificial leaves as a component in this direction. The attention that I put here respect to some of the presentation before is that we need to integrate in this vision also the transformation of biomass, not only of carbon dioxide or the production of hydrogen, which are clearly important components, but only with this we cannot address really the transformation that we need. But to go in this direction, we need also to change, because if we are transforming from a fossil fuel to an intermediate bio-based economy, more or less we can use the actual thermal catalysis. But if we like to go really to the solar-based economy, we need to change the concept. So we cannot just use the concept today of thermal catalysis, because we have what we call a reactive catalysis, which need completely to change also the conceptual basis to go in this direction. And this is part of the general challenge that we have also inside sun energy. And this is another aspect, because we have seen that, for example, also in the previous presentation, we have conversion of either hydrogen to form hydrogen from water or carbon dioxide, or we can include also an aspect that we have not addressed, the nitrogen to ammonia. However, the challenge that we have, if we like to really build a future in a kind of e-refinery, is that what we need is to use all the active intermediates which are formed in this transformation. We can include also methane in this concept, and combine this with bio-based molecules deriving from biomass to make all the kind of advanced approaches. We have seen an example before in which carbon monoxide can be used in carbonylation, but really we have a much, much larger type of effort that we can make to address and to make really this kind of case. So let's now to move what are the concept of decade, which is in this frame, and I think that we are trying to push some novel kind of approach. We have a series of challenges that we like to address. The first is that one of the main problems that we have in all these classical photoelectrocatalytic approaches that we form two different products on the two sides of the cell, and one of these is oxygen, which is often cannot be directly used in mostly of the application that we have, because essentially, especially if we go to a kind of artificial leaves, is very difficult to use effectively oxygen. So can be considered a kind of waste in this term, which reduces the overall efficiency of the system. And of course, we have the other challenge to use solar energy in integration in biorefinery. Some of the concepts that I presented before about e-refinery. And of course, we need to try to develop a flexible solution which can go to multiple markets, because this is very important, especially to be flexible in terms of operations, so chemical and fuels. Associated with this also to improve circular economy and lower the carbon footprint. And to develop also, we need to have economic systems, so we need to develop compact design for the cell, easier scalability, and so on, and realize process simplification. In DECAD project, we are trying to address all these kind of challenges. How is possible? Before, let me say a few words about the kind of approach, because you know that, well, very briefly, we can have many different kind of approach. Very simple, we can have just only classical photocatalytic, in which we have particulate materials. We have separation of the element with anode and a cathode, with anode which can be the active element, or we can have a separate photovoltaic cell which is coupled to an electrocatalytic cell. If we have a look very simple to some of the actual state of the art in water splitting or in carbon dioxide reduction, we see clearly that even if we have apparently some higher complexity of the system, the combination within a separate photovoltaic unit together with an electrocatalytic is between which give the best results. And we have enhanced the efficiency, higher current density, which is very important, and also especially higher stability. This is the reason why in DECAD projects we was fixing on this kind of approach. So what is the input that we are trying to address? We like to address one of the major chemicals which are produced in biorefinery, which is ethanol, bioethanol, and of course to which is associated also carbon dioxide emissions of biorefinery. We have, as I mentioned, a combination between photovoltaic and electrochemical cell. And this is the novel part. We have tried to address to have some product which is formed at both sides of the cell. So at the anode, we have not a water splitting, but ethanol oxidative dimerization to form ethyl acetate. On the cathode, we have carbon dioxide reduction to acetate, which is on-site catalytic transformed react with ethanol to form ethyl acetate. We don't form only this one, we have also some formate formation, and so we have some ethyl formate. However, this is not a special problem because the mixture of ethyl acetate and the ethyl formate in ethanol can be used directly without the need to have separation as a green solvent or as a fuel additive. So we was trying to address in this way all these different possibilities. So essentially, we start from the emission of ethanol and carbon dioxide. We have a cell in which we are using solar energy, and we are producing a mixture of ethyl formate and ethyl acetate, which can be used as a green solver or as a fuel additive. So in this way, we realize, of course, circular economy and also low carbon production. This concept is not used only for ethanol, can be used also for methanol. And in fact, we have one company which is especially interested in application of this concept in methanol plant using the carbon dioxide emission in the methanol plant. This is the concept. You see that we have an external photovoltaic but well integrated cell in the overall system. We have a very compact design. We have an anode and a cathode which are well integrated together. We have a membrane, but this is an aspect that we are evaluating if we need or not. We are using, is not indicated here, but we are using gas diffusion membrane to feed the carbon dioxide in the system. Essentially, we have built the project, try to put all the competence which are needed to try to address this project scheme, going from TRL3 to TRL5. So we have some institution, you see here some of the symbol, and also on the right side, some of the industry or industry-oriented center which are collaborating on the project. So we have a part related to development of the electrocatalyst. There are essentially no information in literature on optimized catalysts which can make the target reaction that we have. We have, of course, a part which is more related to engineering of the system, and UNIC, which provided photovoltaic cell, and so we need the optimal integration between the different components. Then, of course, we have system integration and prototyping. Also here we have a series of companies which are involved in this, and also companies which are involved in market assessment, LCR and other, and then finally system validation with a series of companies that will test the device in environmental situation. We was also putting in the project an external international company which is well known, Professor Domen, which is one of the main reference at the world level on photocatalysis and photoelectrocatalysis. He will act as a kind of external advisor which to benchmark the results of the project in order to validate respect to advances which are at the world level and especially, of course, in Japan. The project is highly integrated. We have at the core prototype validation and, of course, the three element design of the prototype, design of the cell, and electro design, and surrounded by other components from LCR assessment to technical, economic, and social environmental assessment. These are elements which are not at the end of the project, but they are starting already at the beginning of the process, and which serve to guide all the development. We are also at the first year, and we have already first results in this term, which are used to guide and to determine more exactly what are the targets that we need to develop in the prototype and in terms of validation of the results. So for this reason, we have an highly integrated approach. So we have a kind of circular system to go from optimization to scale up and stability validation, having an input some of the results from previous projects, and of course experienced by the beneficiaries, some of the international partners, and of course as output target to go to green solvent and to green fuel editing. We already made some preliminary estimation, and there are very, very good market prospects to go in this direction. Few elements in terms of science. We are trying to design some new kind of gas diffusion electrode, especially which contain some element which concentrate the carbon dioxide at the electrocatalyst surface. So this way we hope also to go to the possibility to use very diluted carbon dioxide concentration, so without the need formally to have a separation and concentration steps. On the term of catalyst, this is one of the examples of the system which are working. Was mentioned before the concept of controlling the hydrophobicity, which is very important. we are working exactly also in this aspect, but we think that is a bit more complex the situation to have the optimization of the three-phase, and we need also to combine this concept with other elements like confined space distribution and other elements. So this is a brief presentation. We are trying to develop a kind of novel photovoltaic combined to electrocatalytic device. We think that this approach is quite useful, and the main element is that we are trying to produce the same product at both sides of the cell element, so at the anode and the cathode, and we think that this model can be useful in many other applications, and of course in terms of market, this will greatly simplify and will greatly improve the economic of the process, because we don't have many different products, but just one final product which can be used also without the need or with minimal downstream operation, because often we forget this element, but the cost of downstream operation is often more higher than the the advantage we have from the photoelectrocatalytic approach. So the idea is to explore the potential use of this novel also to different solutions. We have already one to apply not only to ethanol and so to biorefinery, but also to methanol plants. But we feel that this concept is larger, and we have many different examples in which we can improve circular economy and lower the carbon footprint by this kind of approach. So thank you for attention.
Thank you very much, Gabriel. Now invite all the three speakers to open their cameras. And well, I don't know if you can see my screen, but when I will start reading the questions. So the first one is for Pau Farras from Anna Hankin. What light sources do you use for characterizing upscale systems, and do you always select class AAA simulators?
So we have basically two different setups for our photoreactors. So in the case of the EPFL reactor, this is connected to a solar dish. So it's using natural sunlight that is concentrated. And for the case of the combined reactor, that will be using the light sources from DLR. These are in fact AAA. So these are high flux solar simulators. And depending on the final configuration that we are selecting, we have 2 or 3 different options of different high flux simulators that DLR has at its disposal. So we will then select the type of fluxes that we need for the overall system.
Okay, thank you, Pau. So this is for Professor Senti. Dear Professor, wonderful presentation. Bueno, the person who is asking this is Habib Ullah. What type of material are you aiming for membranes to support high temperatures?
Well, these are, we don't need to have a high temperature operation. So, because we are working at room temperature, so the classical membrane, we will use a bipolar membrane probably also to avoid some of the crossover. However, the plan now is also to try to eliminate the membrane and to design the electrode which can operate without to have any interference on the 2 sides, because this of course will try to improve, well, to reduce the cost in the system. And especially one of the point is that probably we need to go to higher pressure. Up to now we are working at close to 1 atmosphere. But we plan to go to higher pressure in order to improve the productivity of the system.
Okay, thank you very much, Professor. Okay, I have one for Miriam. You have commented before that you are using ionic liquids in your reactor. The capture of CO2 with ionic liquid, would you say it's really a standard procedure, or it's an innovative technique now that has some promising future in this type of technologies?
Yes, there are already several several publications where they are using ionic liquids for capturing CO2, as well as electrolytes also for CO2 reduction. Our system is going to use the same ionic liquid for both processes. So we, in the first beginning of the project, we properly select the ionic liquids to be able to be compatible for both, no? For the CO2 reduction, for CO2 concentration in the capture part of the device, and as well as for as electrolytes for CO2 reduction, okay, because they also have to be compatible with the oxo product that we are generating.
Okay, another one for you, Miriam, from Roberto González Gómez. How you will attach the ruthenium complexes onto the nanoparticles surface?
Yes, usually, actually, we are working with two different approaches. We start with based on the state of the art using phosphoric acid, but we know that for long-term stability this is not the better approach, and we are actually anchoring with saline moieties, which we know that for up to now in the state of the art is the more promising technology in terms of to obtain the less leaching, no? for long-term stability.
Okay, the next one is also for you, Miriam. Are you from Philip Gótico or Gótico? Are you targeting CO2 to oxo products conversion efficiency when finally integrating everything to be on one pot, and then in brackets, envisioning that we don't want to waste any unreacted CO2? Should I repeat?
Yes, I think that the question is that everything is going to be done in one pot.
Are you targeting CO2 to oxo products conversion efficient? Are you telling? I think he's referring of the target on CO2 to oxo products conversion, considering that you are integrating everything to be in one pot.
I mean, in the cathodic part, it's going to be two transformations that are going to take place in the same compartment. The CO2 electro reduction to CO, with selectivity, we know that is the CO product, the CO formation by the electro reduction of CO2 is the more efficient reaction that we have in the literature, because it's the first compound that is generated. So we are pretty sure that we're going to have very good selectivity on that. And the hydroformylation reaction also, it's true that it should work under very mild conditions, room temperature and 1 atmosphere of pressure, but the selectivity should work pretty well. The conversion, of course, it's going to take a bit more, but the selectivity is usually the common selectivity that this kind of hydroformylation process you get. I mean, the linear selectivity for the introduction of the carbon monoxide moiety here. And everything is going to be done one pot, yes.
Perfect. A ver, one from Simelis Hernandez. Thanks to all the speakers for presenting these breakthrough ideas and projects. A question for Professor Centi. What is the starting TRL of the CADI device, and what are the main challenges in the close integration of the PV and the EC devices?
Yes, well, the starting level is the trim in our case, because we have experience on closer related aspect. In terms of integration between the photovoltaic and the electrocatalytic cell, we are working on this for other reaction, and it's still not optimal, but we can arrive to at least 50% of efficiency in integration, which means that we are currently on over 10% of solar to carbon dioxide conversion, and which means that we are in this case still losing some of the energy, but of the electricity which is formed. But I think that this is as an aspect of engineering of the system which we need to still optimize. Essentially what we need to optimize is the optimal potential which is produced from the photovoltaic cell, and the potential which is needed from the electrocatalytic cell. So I think that this is, and of course we need to eliminate any of the resistors which are in the system, but I think that we can arrive to well, a good improvement in this direction.
Okay, thank you very much, Gabriel. We don't have more questions from the audience, and actually we have reached the time for the to close the webinar. I would like to really thank all the speakers for being here today, for these wonderful presentations, for clarifying the questions. It has been very nice, and thank you to all attendees. You can follow the advances and the developments of all projects in the respective websites, and you will be able to have the recording of this webinar plus the presentations soon in the website of the SunCoChem project. So good afternoon, everyone. Yes, it has been a pleasure. Bye.
Thank you.
Thank you. Goodbye.
Goodbye.
Bye. Thank you.